Well, Stuart Beaton normally does these introductions, but this is my visitor. He's been here for the last 2 weeks, so it's my distinct honor and privilege to introduce him. Rich comes to us from the Radar Operations Center of Norman, Oklahoma. The Radar Operations Center repairs, maintains, and upgrades our national network of WSR 88D radars. His education, undergraduate from Auburn University, graduate degree from the Air Force Institute of Technology, both in electrical engineering. He served our country by joining the Air Force in 1971, where he cut his radar teeth as a radar technician. He retired from the military, the Air Force, in 1992, having achieved the rank of major. Along the way, he taught for 4 years as an associate professor at West Point. He started at the Radar Operations Center in 1992 as a chief of systems and hardware engineering and has been involved in data quality work ever since. He gave a keynote talk at the last NEXRAD meeting in Garmisch-Partenkirchen a couple of years ago concerning the topic you'll see now. I met Rich in 2002 when I joined NCAR and became involved in the NEXRAD data quality project, and we've been collaborating ever since, working together. Most recently, he's been here for 2 weeks. We've been working on ZDR, calibration, differential reflectivity, and Rich will explain the rest to you. So let's give Rich Ice a warm welcome.
Thank you, John. I hope I can live up to that glowing introduction with my talk, but hopefully it won't be too long. I do have 47 slides, so if it seems like I'm going through some of them kind of quickly, it's because I don't want to keep you longer than I expect your attention span maybe could hold out. So anyway, as John said, I'm with the Radar Operations Center, or as we like to call it, the ROC. So when people come to visit us, we always say, welcome to the ROC, like the famous movie. So. Nobody knows that movie, I guess. Anyway, this picture on an introductory slide, that is part of our facility there in Norman. In the foreground is the static display, which is the antenna that came from the Norman Doppler that NSSL built in the 1970s, and it was where some of the early proof of concept and research and development work was done for Doppler weather radar, including the development of the pulse pair estimator for determining the Doppler spectrum. So that's kind of a historic piece there. In the background is a typical NEXRAD. Most of you have probably seen the tower with the dome on top. That particular one is KOUN, which was the first article built by the contractor Unisys and installed in 1988, 1989 timeframe. So it's the original production version of NEXRAD. That's currently being operated by NSSL for research purposes, and it's where the first prototyping for the polarimetric upgrade of the 88D was put in the late 1990s. So talking about those dates kind of gives you an idea how long it took for us to get the production dual pol done, because the NSSL had a working research model in the late 90s, and we didn't really finish deployment of the fleet upgrade until about 3 years ago. So it took quite a bit of time to do it. So today, this is the outline of what I'm going to cover. A little bit of history of the 88Ds. I see a lot of young people in the audience, so some of them may not be aware of a time when we didn't have a NEXRAD radar. So I'll give you a little bit of a history. Along the way, we've been partnering with NCAR pretty regularly. John said he started in 2002, but we started a lot earlier than that in 1993. So we're coming up on 23 years of a very helpful synergistic partnership with our friends out here in Boulder. And you see a list of some of the things that were accomplished along the way, and I'll cover those in a little bit more detail. Currently, we are working on the dual pol data quality, specifically calibration. As we'll see, calibration for differential reflectivity is an extremely challenging task, and I'll cover some of why that is. They're also helping us to improve our ability to automatically detect and remove clutter. Those are two big things that we're working on. In the future, we hope to be able to do real-time adjustment of our calibration state for the dual pol radar, and as we get into the later part of this talk, that'll become evident why we probably need to do that. For those that aren't familiar with NEXRAD, it's the U.S. government's worldwide network of Doppler weather radars There are actually about 165 sites. The vast majority of them are in the United States, and here you see the coverage map for the continental U.S. In addition, we have sites overseas in Alaska, South Korea, Guam, Hawaii, etc. The Air Force has some overseas as well as the FAA. And the original deployment was completed. The vast majority of them were done in 1995. There were some sites that were continuing to be put in overseas till 1997. So 95, 97 was sort of marks the beginning of the full operational capability of NEXRAD. I apologize for the cluttered nature of this slide. There's a lot of information on here. It's actually an image of a poster that our director's office takes around to conferences. But it kind of gives you an idea of the timeline of the program. If you look to the lower left corner, 1987, 1988 is when the final sort of design configuration was settled on between the government and the contractors, which is really where the nomenclature for the NEXRAD radar comes from. WSR-88D stands for Weather Surveillance Radar 1988 Doppler. 1988 is sort of the commissioning date, so it dates back that far. It replaced our radar, which was the WSR-57. So from 1957 until really 1995, the National Weather Service was operating a radar that was designed and built in the 1950s. So NEXRAD was a very, very major upgrade. So along this timeline, we've had some major events that have occurred. These just sort of highlight some of the things that we have done to the system to improve it since the early days. The first really major sort of upgrade hardware-wise for the radar itself occurred around 2005 when we went to a digital receiver with open systems architecture computers. The original computers were proprietary super mini computers, and the software was quite limited in what we could do with it. And once that was possible, we were able to put in a lot of new signal processing advances. And NCAR had a role in some of these. For example, the range velocity mitigation technique, which uses phase coding, and I'll touch on that a little bit later, was really started as a partnership between NCAR and the National Severe Storms Laboratory. And all the original prototyping and proof of concept work was really done by the NCAR team. Another major thing that NCAR contributed was the clutter mitigation decision system, which was the automatic ability to detect clutter. And that was an invention that came out of NCAR, and as it has turned out, is our most popular modification that we've done. The field forecasters really like not having to worry about managing the application of clutter filters. So those are two major things that NCAR has done. And I'll touch on a couple of other things as we go along. We look to the future. We're currently involved in a service life extension program. The follow-on radar, which may or may not be a multi-function phased array system, there's a lot of activity going on to solve some of the engineering and science challenges associated with phased array. That will probably not begin production until the 2030, 2035 timeframe. So we have to extend the life of NEXRAD into the 2030s. And so we have a program going on now for replacing the digital receivers and signal processors and refurbishing the transmitter, refurbishing the antenna pedestal and some of the facilities. So we've been basically given a mandate to keep NEXRAD operational until about 2035. So we've still got a few years to work. Some of you younger folks may get a chance to see those days. Okay, so this slide shows some of the major things that we worked on. On the left are the advances that we've put into NEXRAD, only some of them, not really all the things we've done. And on the right column will be the NCAR contribution to that. But one of the first problems we faced in the 1990s was a lack of ability to have really accurate reflectivity calibration. The original contractor didn't deliver a very good system for doing that. The requirement is to achieve calibration to within an accuracy of 1 dB. And we had issues with that early on. NCAR worked with us in terms of solving some of our issues we were having with our solar scans and how to manage some of the large amounts of data that are associated with calibration. So they did a study for us and helped us move towards improving our procedures. The second bullet I call foundational signal processing development. Pretty much everything we do, even today, where we take the digitized output of the receiver, or so-called level 1 time series, and process it through replay or simulation, which is critical for us to be able to develop and validate any new signal processing methods. That all really started here at NCAR with the development of the Archive-1 Data Analyzer, or the A1DA. And I have a picture of that coming up, which is the only one I've been able to find, but it was At the time, in the middle 1990s, it was pretty advanced because the hardware was just not there that could keep up with the data rates that exist within the digitized time series output of a receiver. And even today, the software that is running in our laptop computers that we use at the sites to record time series data, a lot of the roots of that were developed out here at NCAR. So I feel like NCAR really set us up for success in terms of doing signal processing investigations and scientific development with the actual output data of the receiver, as opposed to the level 2 data, which is the output of the radar. So it's been very flexible. They worked with us on integrating the digital receiver, which occurred in the late 1990s, early 2000s. We were able to supply a model of the digital receiver that we integrated into NEXRAD to NCAR for integration in SPOL, the research radar. And we learned a few things by having the team out here really scrutinize the behavior of that system. And we improved the phase stability and the data quality based on some things that were done out here at NCAR. I already mentioned the range velocity mitigation work. They were pioneers in the SC phase code, and I've got a couple of slides on that. And then the big thing, of course, was clutter identification. Along the way, we've improved spectrum width estimates using NCAR algorithms, and they are now actively involved with us in solving some of the challenges of dual pole data quality, including calibration. So the work continues. So I mentioned the Archive-1 data analyzer. At the time the NEXRAD was developed, there were some hooks in the signal processing hardware that would allow the capture of the INQ data out of the receiver. But there was no method of doing it. No recorder was supplied. So we tasked our friends here at NCAR, and this was back when I see Dr. Keeler's in the front row. He was around in those days. Frank Pratt was one of the people that worked on that. And some of the techs here at NCAR, they built this beautiful machine which could tap into various parts of the radar and get the IQ time series data out of the receiver, as well as the antenna position information that you would need to be able to reconstruct the process. And so here you see this. It was essentially two big boxes of equipment that then had cables that had to tap into an interface panel that NCAR designed and built and put in the radar. Here's a picture of the equipment itself. You can see it's 2 stacks high. It has Sun workstation as well as a bunch of custom hardware. And in the foreground here you see my friend Rick Roten, who was an expert on operating this thing locally. And then here is the digital receiver prototype that we first were testing. On the left we have one of our young OU students at the time, Daniel Melendez, and he designed an interface box that would take the angle data from the antenna pedestal, which was coming from this Archive-1 data analyzer, and put it in the format for our digital receiver so that we could passively connect the digital receiver and test it. So the early proof of the digital receiver was done on the KOUN radar with SIGMET RxNet7 digital receiver, but it was made possible by hardware that NCAR had supplied. So that was another area where they were very helpful. So I'm sort of mentioning this time series data because along about that time, and May 3rd, 1999, which I'm sure most of you are familiar, it was a very, very devastating tornado that hit Moore, Oklahoma. It was, at the time, had some of the highest recorded winds. I guess the Doppler on wheels radars recorded very high wind velocities that were not ever seen before. Just so happened that day, my friend Rick was operating this A1DA time series recorder in support of some of the work being done in NSL. So we were able to capture time series data on that tornado. And then that data set has been used numerous times throughout the years in research and development and validation. And what you see here is one example of the use of that data, where we were testing out a spectral clutter filter to replace the time domain clutter filter that came with the original NEXRAD. And so here we have data that was processed through our signal processor without any clutter filtering, and then data here that's processed with the spectral clutter filter, which was the SIGMET Gaussian model adaptive processing. And then we could also process it with the old time domain. And so we were able to basically validate this new filter, but it was made possible by the time series data supplied by the NCAR recorder. There's another example of some investigation work done by NCAR. They took this big box of equipment out to Memphis and collected some data on some anomalously propagated clutter, which you see here. And we were able to use that for testing our various types of clutter filters. So that's another example of the use of some of the early data. As you see the date on here, this is 1997, so it was fairly early in the program. On to range velocity ambiguity mitigation. In 1995, NCAR partnered with NSSL, and they basically were awarded a competitive grant to investigate ways to, sort of get around the Doppler dilemma, where you can either have a nice long range or you can have a nice high velocity unambiguously measured, but you can't have both. But we always want both, so we come to the science community and say, how can we do this? And they implemented this thing called the Sachi-Zernich phase coding process, which is an idea first formulated by Satchidananda of India and Dushan Zernich of NSSL. And so NCAR's part in this was they helped collect some of the first phase-coded time series data to prototype and proof of concept the thing, and they actually published some of the original explanations of how to implement this with this publication here by Chuck Frush, who was working here in the 1990s. And what you see here is an example of the improvement made possible by this phase coding SC process. Here would be the original NEXRAD image with a lot of overlaid echoes where you don't have good velocity returns out on the second trip. And then we have the second trip velocity data recovered using the SC phase code. And again, here's another example of a close-up where some interesting and useful data has been brought out where before it was obscured. But this was all done as part of the early partnership with NSSL and NCAR. So it's fairly significant. And it's one of the things highlighted on that timeline chart that I showed. This is the very first phase-coded data ever collected using a NEXRAD radar. And what you see here, this is the reflectivity image, which has not yet been unfolded by the algorithm. This was data taken in 1997 in Norman on the KOUN radar. Data was collected with the A1DA recorder, and the team was the NCAR team that came out. Frank Pratt was one of the people that came and did that. And so what you see here is a first trip storm, which is sort of mixed up with a second trip squall line. And then the next slide shows the trip separated using the algorithm. So this is the first data set to really sort of be a proof of concept. So I think that's a significant milestone. So that was RV mitigation and phase coding, which was quite successful. Right now, if you look at NEXRAD sites around the country, if there's severe weather going on, the odds are it's running a volume coverage pattern that is running this phase coding algorithm. Any VCP number that you see that starts with a 200 series will be this SC phase code, so it's very popular. NCAR also helped us improve the quality of our spectrum width estimator. This is a spectrum width product collected in Denver, and you see it's in 2006. And the R0R1 indicates that it was the original legacy algorithm, which uses the lag 0 and the lag 1 autocorrelation. This estimator is vulnerable to errors at low signal-to-noise ratio. And also, if you have made an improper estimate of the noise of your system, if you've made a measurement of your radar receiver's noise and it's wrong, it will bias the result here. The NCAR developed and we implemented the hybrid spectrum width estimator, which will basically change the type of estimator depending on the conditions. Do you have a narrow, medium, or wide spectrum width, for example, it will apply a different sort of algorithm. And you can see as I flip back and forth, you get a much reduced variance and a more realistic sort of values out of the hybrid width estimators. That's another very successful thing that we've deployed. So now on to ground clutter, which I think is one of the big things. When we started our grant work with NCAR in 1993-94, one of the big tasks was to help us do what we call AP mitigation, anomalously propagated clutter mitigation. At the time, the NEXRAD clutter filters were controlled by a static clutter bypass map that would be generated offline. And of course, that map, which would basically determine where to apply clutter filtering within the sphere of the envelope of the radar, was only good as the time that the map was made. Because as atmospheric conditions change, the ability of the beam's visibility of things on the ground changes. You have anomalous propagation, which will bring large areas of clutter in. And the people in the field would have to manually adjust, by going onto the computer and applying manual zones to try to apply the clutter filter. And so it was very bothersome and resulted in significant data quality issues throughout the network. And so we had this goal to come up with some way to to identify automatically where we have AP clutter occurring. And the first part of that phase was resulted in an algorithm called the radar echo classifier, which worked on level 2 data and would identify and then advise the operators, where to manually apply clutter filtering. We moved on then to an automatic algorithm that we were running in the RDA itself, which will automatically apply the clutter filters, and that is the clutter mitigation decision, which was developed here. And so I was walking around the halls during my visit here, and I noticed this poster up on the wall out over near John Hubbart's office, and so I had to take a picture of it just to illustrate the slide here. This was described in this radar conference publication in 2009. But what CMD does is it analyzes the content of the signal, both in the spectral domain and in the output product region. It looks at the coherency of the signal, and then looks at things like the texture of the reflectivity, how often does the reflectivity gradient change direction as you go down the radial, things like that. And we initially deployed a non-polarimetric version of that in what we called our software build 10, and it was immediately well accepted, and it becomes the standard that we operate under. Once the dual pole upgrade was done for NEXRAD, we added skill to it by adding some information from the polarimetric variables, for example, the standard deviation of differential reflectivity, and that has improved the performance of it, although we do still have some work to do. We were in the Denver forecast office last week talking to the meteorologist in charge, and we did ask her, were they satisfied with the performance of their CMD clutter detection process, and basically the answer was yes, because they don't have to think about clutter anymore, so it really reduced their workload. So on that topic, this is what it used to be like. The people in the field had to manually control where they applied the clutter. And if you look at this display here is a map of where clutter filtering is commanded within the PPI scope, within the display here of the radar. Right near the radar is constant ground clutter. So this is probably generated by an offline clutter map. But then as things occur, the people in the field would have to apply these zones. And I think this operator probably was late one night and was getting tired of having to do it, and so they just sort of started sticking clutter filtering in anywhere they wanted, including this little frowny face over here. So I like to show this as an example of why you don't want to expect people in the field to manually track, because they kind of get frustrated after a while. So this is my example I like to show. An example of why it's important to properly identify and remove clutter is illustrated in this figure that's from the Friedrich paper, where they took clutter contaminated data and clear weather data, and they combined it in various ways and ran some simulations and looked at the bias effects on the various products, the reflectivity, the velocity, the differential reflectivity, correlation coefficient, and so forth. And they used a couple of different models, and they generated this sort of band of acceptability where you need to identify and remove clutter down to these sort of clutter to signal ratios. So here 0 would be clutter power would be equal to weather power, and here would be clutter power is a tenth of the weather power. And so for the original sort of Doppler and reflectivity things, it wasn't really a problem as long as you could identify it to where they were about equal. But for some of the polarimetric variables, for example, correlation coefficient, you need to be able to find and eliminate clutter down to some very low clutter to signal ratios. Here is a simulated performance curve of the CMD published by Ellis and Hubbard. And if you look at this, this is the probability of detection where you apply the clutter filter and you don't apply the clutter filter. And the 50% probability point here is about at the -10 to -13 point. So we're sort of in this region here right now. So we do pretty well with CMD for most of the variables, but we do have some reports from the field where they're confused about residual biases that occur in the correlation coefficient. And so we're working on a project that they've deemed the clutter footprint. That's what our hotline meteorologists call it. So sometimes we see when under certain conditions there will be some bias in the correlation coefficient. So we're working with the NCAR team to try to drive down the detectable range of this, try to improve the detection performance. And so this is an area where NCAR has been quite visible. This is an example of some of the performance of CMD data that we took during the engineering validation. This is data from here they're in the Front Range area from the Denver. Here's reflectivity with no clutter filtering, and you can see the mountains there. And then the automatic clutter detection CMD has picked up these regions as being highly probable to be clutter, the little gold areas here, and so the clutter filters will be applied. And this would be how it would look under control of the automatic detector, CMD. And then typically what happened before we had CMD is people would get tired of putting these zones in and they would just say, well, filter everywhere. Let's just filter the whole range. And you can see what can happen here along the area where the velocity is near zero in this particular scan. The clutter filter, it takes out most things that are near zero in the Doppler spectrum, and so it takes out the power along here. And see this little storm here got cut in half. So we don't want this, and we do want this, and this, fortunately, this is what we have most of the time. So now the big topic, differential reflectivity calibration. We've been working on the operational version of dual pole for NEXRAD for over 10 years. For most of that time, we've been aware that we were going to have a problem with calibrating the radar such that we could get the most accuracy out of the differential reflectivity. And so this is another poster I saw on the wall, which is one of my favorite publications that I referred to a lot. Hubbard, Pratt, and Dixon published this uncertainty of ZDR calibration. And it really sort of summarizes the engineering challenge, and so gives us a good reference source for when we make decisions about where to put resources in terms of investigating hardware or investigating external methods for assessing the calibration. So these are all the sorts of things that NCAR has worked on in terms of calibration over the years. In the early days, through this work that they did investigating the uncertainty of the hardware testing, they were quite helpful in helping us deal with the contractor when we were in things like critical design reviews, when we were assessing the dual pole contractor's performance and their test methods. So this was helpful. They actually attended some of our critical design reviews and helped us deal with the contractor. The uncertainty analysis was a big thing. On that topic, basically we had funded NCAR to do a lot of investigations using S-Pol, including supplying some hardware for automatic test equipment sort of things. And if I recall correctly, at the time, the general conclusion was that with on-equipment hardware type test measurements, your uncertainty overall would probably be not much better than about 1/4 of the dB. And it's just because of these uncertainties from all the different hardware measurements sort of add up as you go along. And I believe that's been sort of proven out in our experience with the production system. So that has led us to looking at external targets as a way of assessing the performance of the radar, and I'll get to that in a minute. Along the way, there were some novel methods discovered, one of which is the cross-polar power method, which we've been attempting to implement on NEXRAD, and there'll be more on that in a minute. So what is ZDR calibration? A polarimetric radar is basically looking at the return power from two different polarizations that are transmitted by the radar itself. In our case, we transmit a horizontal polarized wave and a vertically polarized wave simultaneously. So out here in this little cartoon thunderstorm, we'll have rain, which will have some characteristic ZDR. The larger the drops, the higher the ZDR will be, because the axes of the flattened out raindrops, the horizontal axis is larger than the vertical axis. And so there's an intrinsic measurement out here that we're trying to retrieve. But we're using this imperfect system called a radar, which imparts an error, which we call bias. And so the actual measured ZDR, which is the power ratio coming out of the receiver, is clouded by this machine, which is interposed in between the intrinsic value and the measured value. And so calibration is the process of determining what that bias is in the hardware. How accurately do we have to do it? Well, there are numerous papers over the years where the general consensus of the research community is that you need to be able to measure ZDR to an accuracy of 1/10 of a dB or better. And there's a good illustration of that in the Bringy and Chandra text, figure 8.8, where they show these contour lines are the errors in your rainfall rate estimates, where you were using reflectivity and differential reflectivity as your input parameters. And this box here, where I've drawn, shows our current requirement, which is to maintain reflectivity within plus or minus 1 dB and ZDR within plus or minus 1/10. And you'll see that down here, where you have an error of +1 in Z and -0.1 in the ZDR, you can have a 30% error in your rain rate estimate. So if we want to keep rain rate estimates from the algorithm down to acceptable limits, we have to maintain these. But as it turns out, the 0.1 dB is very difficult to achieve. Remember earlier I said the hardware analysis alone says our uncertainty would be about 1/4 of a dB. So we're not going to get there with on-equipment measurements. So how do we determine the bias? As I said, we make measurements on the hardware, which has been deemed the engineering calibration. Traditionally, research community has used vertical scanning and light rain, or what Professor Chandra calls the symmetry of scatterers. And then there's a whole lot of work going on in just basically looking at the targets themselves, the returns from rain, from snow, from Bragg scatter, from ground clutter, from the sun. All these sorts of things are examined in great detail to try to assess the performance of the radar, and we are doing that. And then finally, for a future thing, we hope to implement this cross-polarization power technique. And so there's my favorite illustration of the vertical scanning in light rain from the Gorgucci paper. Unfortunately, NEXRAD can't do that. The hardware design of the antenna pedestal doesn't permit vertical pointing. We also have a radome with lightning protection and cables and obstruction lights and things at the top, which would bias the result. And finally, we decided early on that we didn't think that it would go very well to interrupt operations in order to do these vertical scans. So at present, we don't do it, although we may reconsider that at some point in the future. So this is a diagram of our system talking about the hardware problem. There are basically three elements to calibration. There's the transmit power bias, there's the receiver channel bias, and there's the antenna bias. These things are sort of actively changing over time. The transmitter power is not always equally balanced. The receiver channel, the difference in gain between the horizontal and vertical will change as a function of temperature, for example. And so we have to have a way of monitoring this. And so in the NEXRAD, the whole calibration scheme revolves around these waveguide couplers, which allow us to tap out signals from the waveguide to measure the transmitter power, as well as to inject test signals to characterize the receiver. And so we have this elaborate hardware scheme where we determine all of these calibration parameters. And I won't go into the detail because there really isn't time, but again, this process has an overall uncertainty of at least 1/4 of a dB or more. So we're not going to get to our full accuracy just by doing tests. For the antenna portion, which is here, the only way really to measure the characteristics of the antenna is with the solar scans, because it's just, we have 165 sites, we can't do antenna pattern measurements at every site. And as we'll see, the characteristics of the antenna tend to change over time. So we rely very much on the sun to do that. And so here's just an example of a hardware measurement. These couplers, we have to know the coupling value of the individual pieces of hardware. And this is manufacturer data, which the little X's here indicate what the manufacturer says the coupling value is for different frequencies across our band. And if you look at this scale over here, this is 1/10 of a dB right here. And we have widely varying measurements just from the manufacturer. So this is sort of proof that we're not going to get there with measurements. And this is, again, another illustration from the NCAR publication in 2007, which addresses this uncertainty of this coupling value. And so we have a pretty good handle on what the problem is. We just don't really know yet how to solve it. Solar scan basically consists of scanning the disk of the sun, which is pretty well understood to be non-polarized. There's no preference to any particular polarization. So we can use that as a way to assess the receive bias of our antenna portion and the receiver. This ratio of the power seen from the sun should give us a measure of what the bias is of the receiver paths. And so we do that with NEXRAD. We have sort of a crude method where we simply scan horizontally once through the expected position of the sun, vertically once through the position of the sun, and we fit these parabolas, and we try to come up with positioning accuracy as well as the peak gain and the differential bias numbers. This current existing method is subject to error, and I think is another source of the errors that we're having with ZDR calibration. We are planning to implement a so-called box scan, which was developed as part of the NCAR's development of the cross-polar power, where this is routinely where you scan two-dimensionally across the disk of the sun, and this indicates the sun's H power. And then it allows you to more accurately determine the center and the peak, as opposed to just taking one pass-through like we do now. So within the next year or two, we'll be implementing something like that in NEXRAD. It's important when you're looking at the bias between the H and V channel to be centered on the sun, because if you look at this sort of standard literature reporting of the microwave power of the sun, it's about the size of our half-power beamwidth of the antenna. And so if you don't get centered on it, you're going to get a bias. This is data that came from the 1960s, where researchers used very large radio telescopes to get high-resolution images of the microwave emissions of the sun. So all of that says that we have trouble meeting our 10th dB requirement with the measurements that we make, so we've gone to looking at external targets. We now look at the data itself. We look at returns from the rain, from ice and snow above the melting layer, as well as Bragg scatter and clear air. And so in the rock, we have implemented a monthly monitoring program for all 165 sites. In the radar product generator, every volume of data that comes in is being examined by these algorithms. And estimates of the bias of the radar can be obtained from these returns if the correct and acceptable sort of return is discovered. And so during the right conditions, pretty much every volume scan, we get an estimate of the radar's bias. These estimates are then combined into 3 to 6 hour events, and then the sum total of the bias for an event will be reported. And then we analyze a sort of a 6-month history. We currently have set a criteria of plus or minus 0.2 of a dB to determine if, resulting from these external estimates, if we have a site that is within our acceptable performance or outside of our acceptable performance. The reason we picked 0.2 is because we really think that's about the limit of the external method as well. So about plus or minus 0.2 is about as good as we think we can do. But so we produce these charts every month for every radar site, and we supply them to the regional directors of the Weather Service and also the FAA and the Air Force. And here's an example of a site that would not really require any maintenance activity because it seems to be within acceptable limits for for all the rain estimates and the Bragg snow estimates on the Bragg. But we have a site here, an example of one that has got a low bias that's outside our acceptable limits. This site would appear on a list that would be sent to the regional directors. The regional directors would then work with the field sites to have some maintenance action taken, perhaps to improve the performance. So I mentioned that we have 3 methods, and this is a little cartoon graphic of how they differ. It's pretty well known that if you have the right sort of light rain, you have an expected or intrinsic value of ZDR. There can be limits to that, exceptions to that, but we have a set of values that we use for the expected value. Up above the melting layer, if you get the right kind of conditions, you can get an intrinsic value of about 0.2 of a dB, and that is a little bit more accurate. And then finally, in clear air, if we can find Bragg scatter, which means, when I say find, it means that the conditions are right and it's not contaminated with insects, for example, and the signal to noise ratio is sufficient, we can use that. And Bragg scatter has an intrinsic ZDR value of 0 dB, so that makes it pretty easy to determine. Of the 3 methods, I think the light rain is probably the least accurate or the most variable. We get better performance with the dry snow and ice, and then we get pretty good accuracy with Bragg if we can actually get Bragg, which we can't get everywhere. On the topic of using the rain, this is an example that I like to show. What we have here is a plot of Z versus ZDR for every volume for a rain event that occurred in Oklahoma City a couple of summers ago, July, and you can see that when we have the right sort of pure rain going on that's being captured, the plot of Z versus ZDR sort of follows this grouping here. And then based on the recommendations from Alexander Ryzhkov, the yellow triangles here represent the numbers that we expect to see within these bands of reflectivity. And so if we collect the statistics and we can basically then subtract these numbers, and the result would be then the bias of the radar. And you can see for this event, they center kind of nicely, but on a volume to volume basis, they don't fall on there. So it would be nice if we could come up with a way to sort of dynamically reallocate these things. This is just an illustration of Bragg scatter from Melnikov's publication. You can see the Bragg layer here. It should be near 0 ZDR. And here's an actual data set collected from a NEXRAD where the peak value of the histogram of the Bragg is here, which this radar is obviously calibrated high. There's a nearly 3/4 of a dB error. So this allows us to look at it and go, oh, we need to work on that. We also look at the accidental interception of the sun through the sun spikes. A couple times a day, morning and evening, we get multiple hits of the sun. And based on the publications and research by Holland and Huskinen and others, which are illustrated here, we can look at the identified position of the sun strobe and compare that to where the astrophysics community tells us the sun should be, which is pretty well known, and then we can plot that error on a hit-by-hit basis. And so if we see a sun spike and we plot it here, this represents the error between the expected position of the sun and the reported position of the sun. And in individual cases, there will be errors because we don't always hit exactly the center, for example. But over time, we should collect enough data to indicate whether we're pointing in general accurately. Here's a case where a NEXRAD radar is well calibrated in terms of pointing, and here's one where the pointing error is low, and so we can see that from the solar strobes. Also, the return should be 0 dB ZDR because it's the sun, and so if the value is not near 0, then we have a receiver bias. And this is just an example of a sun spike with some weather. And then the blue represents the power received. So you can see this weather signal here. And then we also have an algorithm where we automatically determine the noise on a radial by radial basis. And you can see here's the noise power of the sun quite nicely detected here. And this is what we use now. We use a noise estimate to do that. So on to S-pole and some of the current things that are going on. I mentioned this cross-polar power. I'll show this here in a second. We have observed, not just NEXRAD, but other radars as well, we have observed that there appears to be something of a temperature dependency of the antenna performance. And this is not picked up by any way other than looking at solar scans. And so they were doing a lot of that with S-pole. I had this idea recently, since S-pole can be very precisely calibrated using vertical pointing, cross-pole, various other methods, that when we have S-pole operating in an umbrella area where we have common volumes that we can scan with NEXRAD, we may be able to use S-pole as sort of a standard to assess the accuracy of our own calibration methods that we're using for the various NEXRADs, and so I'll show some of that. Cross-polar power, I apologize for not putting the reference on here, but this was basically extensively described in a couple of publications that John Hubbard did in 2003 in the JTEC. He's sort of the guru of this process, and we've been working with him for several years to look at it on NEXRAD. It consists of either alternating or transmitting an alternating H and V signal, or transmitting an H signal for some period of time and then switching and transmitting a V signal, and looking at the cross polarization channel, the cross polar power coming back from a patch of ground clutter, and then looking at the ratio of those two things. Because of reciprocity, the transmit H receive V power should be the same as the transmit V receive H power. And any difference in those two would be related to a bias in the radar system. That's sort of the basic concept. Along with that, there is a solar scan portion of it, which looks at a sun ratio, which picks up some other elements. And this has been demonstrated on S-pole to be equivalent to the vertical pointing, which is sort of the gold standard. And so that tells me that if we can implement this on NEXRAD, then that might be a proxy for our inability to do vertical pointing on NEXRAD. So we've been pursuing doing that for a while. Here's an example of the cross-polar power ratio scatter plot from S-pole, where I believe this would be maybe alternating in rain, and this, I believe, was the slower switch process, which Dr. Hubbard describes, where you transmit a sweep of H and then you transmit a sweep of V. And the reason they were investigating looking at this is because that's how we're going to have to do it on NEXRAD, because we don't do alternating transmission. You can see that you can get various spreads in the standard deviation of these powers. And then over here is our attempt to implement it in NEXRAD. And so you can see we have a lot more spread in the cross-polar power ratio. And the reason for that is we have a different sort of means of controlling the antenna. We don't have the elevation control stability that we need to be able to guarantee that we meet the reciprocity assumption for the ground clutter return. We're addressing that. The new digital receiver signal processor that we're beginning deployment on will have an improved elevation scan method, and so we're going to revisit this and see about implementing it. As part of all of our cross-polar development and implementation, we did a lot of sun scans because the solar box scans is part of the process. And on the radar there in Norman in December of 2012, which is now coming up on 4 years, we took a week's worth of solar scans. Anytime the sun was visible, we would do this box scan. And we were quite puzzled by the results because we have this diurnal swing, which really shouldn't be, because any changes in the receiver channel are taken care of by our test signal injection on every volume. And so this, we were wondering, why is the antenna doing this? The antenna bias apparently is changing as through the day. And here's sort of a close-up view of it. We attempted to correlate it with radome temperature, and so here's a scatter plot of radome air temperature and the bias. There doesn't appear to be a strong correlation. This could be because our temperature measurement is very inaccurate. It's just like a thermostat type measurement, so it's not very good. So that, I think, inspired John Hubbard to look at it pretty closely using S-pole, and in a couple of field programs, taking lots of solar scans during both the winter and the summer. This has been observed on the S-pole antenna. So it's really not just unique to NEXRAD. And so here's some data that was from Pecan last summer, where where the cross-polar power ratio was taken to get the system bias. And then they also did the above the melting layer scanning the ice or the snow, I guess in our case. And you can see that there is this diurnal swing that occurs in the ZDR bias. It's pretty obvious. And so this is the thrust of current research on S-pole. One of the things we have to be careful of is if we're comparing results on S-pole to NEXRAD, we have to be aware that there are differences in the antennas. S-pole has a nice symmetrical feed strut assembly, whereas NEXRAD has a tripod and a radome, and then the actual design of the reflector is different, so we'll be aware of those sorts of things. So currently, what are we doing? The work is being funded at NCAR through basically a contract with the company that I'm currently working for, Centuria, which is the support contractor to the ROC. And there are three major tasks, one focusing on this ZDR calibration, where they will help us implement cross-polar power and help us implement the solar box scan. This hybrid spectrum width estimator, which was so successful, now has to be integrated with our new staggered PRT, which we're about to deploy, which was developed out at NSSL. And there are some new ways of doing the autocorrelations associated with that. And so we're working with the NCAR team to integrate the new width estimator into that. And then the third tasking is related to general polarimetric variable data quality, where we're looking at improving the CMD detection and getting a better handle on how accurate are our external methods using the rain, the snow, and the brag, et cetera. So we're currently working. So I've been here for a couple of weeks. It's been very interesting to be out here. I learned how to use some of the NCAR software to look at the Pecan data set. So I pretended I was a researcher for a couple of weeks using a tool developed here, the CID tool, CIDD, which I still don't know what it stands for, but maybe somebody can tell me. Mike, I'm looking at you. So anyway, here's a time last summer during the collection where S-pole collected this storm data. And down here is the KDDC Dodge City NEXRAD. So here's a picture of it here. And so I looked at this and realized that this region here is sort of about 50 kilometers between each radar. And so I'm interested in how does the KDDC data compare to the S-pole data, which my assumption is S-pole will be calibrated. And so if there are differences, that indicates a calibration issue perhaps with the NEXRAD. And so I did these cross sections. We have the KDDC sort of artificial cross section done by the software using the level 2 data that came from Dodge City. And then the software allows you to make a cross-section equivalent, but doing it on S-pole data. So when I do that, this is what I see. This is ZDR. And so here's the Dodge City radar, and here we are at about 50 to 60 kilometers away. There's some rain there. And then the same region, if I've done it correctly, which, I'm novel, I'm new to it, so I might have not done it right. But this sort of looks right. You can see the ZDR reported by S-pole. And so if I look at these two, clearly the Dodge City radar is indicating not only is it more noisy because it's using fewer samples to make the estimate than S-pole would have been, but it's also in general seems to be presenting a higher value of ZDR than the assumed well-calibrated S-pole. So this would be my standard, this would be my observed. I was just trying to sort of prove out, was this possible to do this? We'll be a much more sophisticated approach later to do it, but it looks to me like this might be something we can do. And so then I went and and there's the illustration of the regions, 50 kilometers about from each. And so then I went and went back in our historical database and I pulled out this external estimate, the so-called shade chart that I showed you earlier for the Dodge City radar for that period. This would be February to July, so this would be middle of July. And sure enough, based on our own methods, we see that KDDC has a high bias, which sort of explains the difference in the ZDR. So to me, this, a lot of further work needs to be done, but I think we could possibly, anytime we have S-pole collecting data within the range of a NEXRAD, we should be looking at it because it helps us learn something about, for example, the accuracy of these methods. So anyway, so that's Dodge City. This week also, last week and this week, they've been running S-pole to do a lot of these solar box scans, investigating this temperature dependency. So, for example, here is a set of scans that was made in the morning, one day last week, and then in the afternoon. So we have the horizontal and vertical power here. You can see there's a slight elongation in the vertical channel, which has been seen before with the S-pole antenna. And then if you look at the power difference, you see right here in the center, this would be the receive sort of ZDR measurement. And you can see there is a slight difference from morning to evening. And then this is the S1, S2 product, which is part of the cross-polar power. And so the team here will be doing lots and lots of these to try to get a better handle on it. From the Pecan data last year, when they made many, many solar box scans, this is sort of the result that they came up with in terms of the temperature of the dish, which they instrumented, as well as this S1, S2 ratio. And you can see there's a definite relationship. And this has driven them to come up with this regression analysis. So you actually, knowing the temperature, you could possibly improve the real-time calibration of the system for your antenna. And so it may be sort of a long stretch to see if we can actually do that with NEXRAD, but I think we need to pursue making these kind of measurements with all of our NEXRAD systems so that we can do a better real-time upgrade, real-time analysis of our bias. And with that, I'm going to leave that as my last slide because that's where we're at right now. The research has come to this point where they're working with us to improve the calibration of NEXRAD. I hope to someday be able to do almost a dynamic adjustment on at least an hour-by-hour basis, perhaps, based on some of the research that's come out of NCAR and what we'll work with them. And so for that, I'm done, and I took 50 minutes, and maybe we can have some questions.
Thank you, Rich, for that interesting presentation. So if you have a question, let me hand you this mic, and so that this is being recorded, so your voice will appear.
Oh no, Jim's going to ask a question.
No, Rich. I remember at one of the TAC meetings, I brought up the question about the NEXRADs being able to really point vertically. And I think it was you at that time said, maybe we can do that without too much expense. Mm-hmm. Has anything been done since, or?
We had a recent question from the FAA on that, and so we presented them with the list of things that would have to be done to be able to do that. The antenna, it's certainly possible, and let's see, I don't know if we can see the picture from here or not. Yeah, if you look here at the NEXRAD antenna, these are the stops that keep it from going too far down or too far up. The 60 degrees is the upper limit of the hardware. But these things can be removed. So certainly it would be possible mechanically to do it. In addition to that, there are some, since the dual pole upgrade, one of the components known as the RF palette, which is where the transmit power is divided and the receive signal circulators are all done, would have to have some modifications made because there's an interfering piece of waveguide. So, but it could be done, certainly. A bigger problem would more likely be what would be the issue with the radome, because most of the sites have a lightning protection device at the very peak, and there's a hatch with aircraft obstruction light, and there's cables and things. So we would have to look at modifications to the radome, or get a handle on what's the error due to that near field obstruction there. But it certainly could be possible. And I mentioned one of the reasons we sort of avoided doing it is because we weren't sure of the interruption to operations, how often we would be allowed to do it during operations. But I'm encouraged by the reports I'm getting from the Germans. The DWD, Dr. Freck is here, has been working on that, and they do vertical scanning quite often during their operations. And it doesn't seem to cause much of a delay. It seems to be a pretty good way to keep a handle on your system performance. And as well as he's recently been investigating that you can actually get some operational benefits from doing a vertical scan every once in a while. This is tied into some of the work that Alexander Rizkov's been doing with the QVP, the quasi-vertical profiling. So it may be, I wouldn't rule out the possibility that someday maybe it could be done.
Other questions? I knew Jeff would have a question.
Yeah, Rich, regarding the data quality and the better calibrations of the radar data, those of us in the research community know that it's important to have a calibrated radar, and I'm wondering, and one of the primary goals is to come up with better rainfall estimates.
Right.
So I'm wondering, what kind of input do you get from the forecasters in the field, the radar users? How important this is to them, and do they say sometimes, I wish you could get the rainfall rates better, and what other kind of benefits show up from improved data quality.
Right. Well, the big improvement obviously is in the rainfall rate estimates. Now, I don't really work in that area too much since I'm not on the hotline talking to the field every day, and I'm not in the applications branch, which deals with that. But I do know that it's been considered one of the top couple of priorities of the program for some time now. So I know that there's also research going on, however, into other means of doing the estimate where you're not so dependent on ZDR. You know, the attenuation-based ones, for example. There's a lot of research going on there. The other thing that bad ZDR estimates do, of course, is it affects your hydrometeor classification. You can have some errors there, too. So at the same time, on the engineering side, where we're trying to give a better estimate, the algorithm people are trying to make their algorithms less vulnerable to data quality issues. So there's works going on both sides of the equation. We've had a team working on calibration at the Rock for some time now. 2 years ago, we wrote a report and we identified 26 areas where we could improve the performance of calibration. And we've been systematically plowing through that list since then, and we've implemented quite a few improvements. Every month, the Rock hotline sends emails out to the regional directors identifying the sites that appear to have had a problem. So overall, we think the network is generally sort of trending towards tighter calibration, but it's taking time to do it. It's been largely an educational process too. So, but we do monitor that every month. We monitor the statistics and we talk to the field. And but some of the engineering changes that we may make may also improve things. So, for example, the hardware calibration. One of the hardware calibrations requires the technician to disconnect and reconnect cables, and that introduces errors. And so we're looking at automating that with switching network. The other thing is this, I think a big source of our error may be the way we're doing solar scans now. Once we implement the box scan process, I think we'll see an improvement. So, but you know, it's been slow. It's a complicated problem. 1/10 of a dB is a ridiculous requirement. When I first, you know, I'm an old microwave guy from the vacuum tube days in the 70s, and if we got something within a dB, we were happy, you know.
Anyone else? If not, let's give Rich another thank you.